Let's discuss the topic of time dilation. What is time dilation? Well, have you ever heard or have you ever wondered if time flows the same for everyone? Einstein's theory of relativity tells us that it doesn't. Time dilation is the idea that time doesn't tick at the same rate for everyone. It depends on how fast you're moving or how close you are to a massive object. Let's start with section 1 and let's find out the different types of time dilation. We have two main types. The first one is called special that is special relativity, and the other one is general. And this is general relativity. Okay, first let's talk about time dilation caused by speed, as described by Einstein's theory of special relativity. When you move close to the object at the speed of light, or when you move close to the speed of light, time slows down for you compared to someone who's stationary. Let's imagine it this way. Let's imagine one figure on Earth. Let's imagine this as a rocket ship. Let's say that a stick figure is inside here. Now, this ship is moving at 0.9 c. C just means that this just means that it's moving at 90% the speed of light. Imagine this. You're standing on Earth while your friend is traveling in a spaceship at 90% the speed of light. For every second that passes for you on Earth, less than a second passes for your friend on the spaceship. So when time passes slower for him or for her, this means that your friend would be aging slower than you. Let's call this stick figure the Earth observer. Let's call this one the spaceship observer. That's it. Simple. Now, on Earth, 1 second would always be equal to 1 second. No doubt. But for the spaceship observer, on the other hand, his 1 second would be equal to probably 0.5 second. This difference happens of because at high speeds time tends to stretch out. This is called time dilation. The faster you move, the slower time flows for you compared to someone who isn't moving as fast. This is shown by Einstein's time dilation formula. This is where time t is just the time for someone stationary. T this way explains this is time for someone moving at v. This is nothing but the speed, and c, as seen before, the speed of light. Let's put it that way. Now let's take an example. If astronauts traveled at near light speeds to a distant star and came back, they would have automatically aged. Now let's take an example. If astronauts traveled at near light speeds to a distant star and came back, they would have aged much less than the people on Earth. This idea inspired movies like Interstellar, which we'll talk about in a second. Now we can move on to talk about general relativity. So the second type of time dilation comes from gravity itself. Einstein's general theory of relativity tells us that massive objects like planets or black holes warp space-time around them. This warping affects how time flows. Let's take this for example. Okay, and let's say this is a grid. And let's say this is Earth or a black hole, and it's curving space time itself downwards. Bear in mind, this is not the sun, this is Earth, or a black hole that is, and this is a warped spacetime. So now the closer you are to a massive object, the slower time flows for you compared to someone farther away. We have discussed that. So now let's take two stick figures again. Now this figure on Earth, he is on this figure is closer to gravity, and let's just say this figure is just floating away in space, far away in space. Here he is. This clock moves at slower pace, while this clock moves at a faster pace. For example, if you live near a black hole where gravity is extremely strong, time would pass much slowly for you than someone far away from it. Let's bring out an example. And this can be further elaborated by it actually happening on Earth. Global positioning systems or GPS satellites orbiting above us experience a weaker gravity than we do on the surface. Their clocks tick slightly faster than ours, and scientists have to account for this difference while calculating GPS positions. Let's move on to section 2. This is speed, and this is this overlapping part is nothing but the time dilation. In reality, both effects, speed and gravity, can happen together. For example, astronauts aboard the International Space Station experience both types of time dilation. They're moving fast. They are moving fast around Earth. This is related to the special relativity. But they're also farther away from Earth's gravity, as we've discussed, which is the general relativity. These effects combine to make their clocks tick slightly different, differently from ours. Let's move on to the third section. Let's once again represent, visualize this with the grid. This is nothing but space-time. So, so to understand why this happens, we need to talk about space-time, or the fabric of our universe. It basically combines space and time into one thing. Like we have used Earth before, let's consider a black hole. And these lines bend because of gravity. With these lines. These lines are bending because this is a massive object. So when space-time bends due to gravity or motion, it stretches out time itself. This means that what feels like 1 second for me might feel like half a second for someone else. Now we can move on to the fifth section where we talk about this brings us to one of the most famous thought experiments in physics, the twin paradox. So these are two twins. If one twin stays on Earth and the other travels through space, again at the near speed of light, that is meant to be a rocket, but okay. Yeah, so if one twin stays on Earth and the other travels through space at near light speeds and comes back after many years, they'll find something shocking. The twin who traveled will be younger than the twin who stayed behind, even if on Earth they were born at the same time together. This shows how time dilation can lead to real differences in aging. Now let's bring this to one of the final topics. Well, this is meant to be section 5. Let's go on to section 5. Well, then we might wonder, why does time dilation even matter? Well, time dilation isn't just theoretical. It has many practical applications. Like we've discussed uh, previously, firstly, global positioning systems, or GPS satellites, use corrections for time dilation caused by both their speed and the weaker gravity compared to Earth's surface. This also helps scientists who study on black holes. Yeah. This also helps scientists studying black holes rely on time dilation effects to understand how these cosmic giants work. And who knows, in the future, understanding time dilation could help us explore distant stars without aging much ourselves. Well, now let's bring all of this to an example. Time dilation in Interstellar. Now let's bring everything we have learned about time dilation into focus. Let's look at one of the most famous and extraordinary examples in science fiction, Interstellar. In the movie, Cooper and his crew visit the Miller's planet, which orbits dangerously close to a supermassive black hole called Gargantua. What happens there is a perfect example of Einstein's theory of general relativity in action. Let's visualize this. My drawing. I'm making this a grid. Now let's say this is Gargantua. And in this grid, this warps space-time because it's a supermassive black hole. Let's say this is the Miller's planet. Time dilation on the Miller's planet happens because it's so close to Gargantua, this supermassive black hole. According to Einstein's general relativity, as we discussed, massive objects like black holes warp space-time. The closer you are to such an object, the slower time flows for you compared to someone farther away. In simpler terms, imagine space-time as a stretched rubber sheet. Gargantua creates an enormous dent in this sheet, and the Miller's planet is sitting right at the edge of this dent. The intense gravity causes time itself to stretch, so much so that 1 hour on the Miller's planet equals to 7 years on Earth. Well, in Interstellar, Cooper and his team just spend over 3 hours on the Miller's planet. But when they return to their spaceship orbiting farther away from Gargantua, they discover that 23 years have passed on Earth. This extreme difference happens because of the immense gravitational pull of Gargantua near the Miller's planet. While time crawls for Cooper and his crew, it races ahead for everyone else further away from the black hole. Well, this should raise a very interesting question. Why doesn't time just stop completely? That you might wonder. If Gargantua is so massive, why doesn't just time stop on the Miller's planet completely? Well, that's because the Miller's planet isn't right at the event horizon. Let's say this circle is the event horizon. This event horizon is nothing but the point where nothing, not even light, can escape from the black hole. It's close enough to so this shows that the Miller's planet is close enough to experience extreme time dilation, but it's far enough to avoid being pulled in completely. Well, now let's summarize. So, what does Interstellar teach us about time dilation? It basically shows that massive objects like black holes warp space-time, causing drastic gravitational time dilation. And then you can see that the closer you are to a massive object, the slower time flows for you compared to someone farther away. Now, this isn't just science fiction, it's also real. As we discussed, we see smaller effects on time dilation with satellites and astronauts today. Right. So, coming to a conclusion, time dilation shows us that time isn't absolute. It depends on where you are and how fast you're moving, making it relative. And Interstellar manages to dramatize this concept rather beautifully.